obviously. And I lied to you. I think I told you we were only going to talk about hikes in Arkansas last time I showed you a picture, but this one is actually back in Tennessee. So it's around Nashville area. The fun fact about this waterfall, though, is it's the largest waterfall east of the Mississippi. So it's in an area around Nashville called Fall Creek Falls. Right there. And if you go to this area, there's really good hiking. There's really good bike trails to ride on, pretty flat stuff. And then this is not the only waterfall. There's many waterfalls in the area to look at. So I don't know if you can hike to the bottom of the waterfall or not. We just did some like rim hiking kind of around this region area, around close to the waterfall. But it's a really pretty, and it was a really fun day when we went out there. So, okay, solutions. Oh, I forgot to tell you, this is a 256-foot drop. That is the largest east of the Mississippi. So that's how big it is. Okay, solutions. We're going to start off with this figure. And this is all, by the way, corresponding to Chapter 9. So we're officially in Chapter 9. You might recognize this figure from the very beginning of semester. We started in Chapter 1 talking about matter, right? And how to classify matter. And we use this figure at the end of Chapter 1, or maybe the end of the very first day, to talk about how we classify matter. And we started off asking questions like, okay, if we have some matter, we want to classify it. If we ask this first question, is the composition constant? If the answer was yeah, then we have like an element or some kind of pure substance, whether it's a compound or an element. If the answer was no, meaning the composition is not uniform, maybe there's more than one thing present in our matter, then we have a mixture. And there's several examples. We also learned that there's two kinds of mixtures, heterogeneous and homogeneous. Y'all know my favorite example of a homogeneous mixture is ice cream, just plain vanilla ice cream, which, by the way, I'm trying something, not for me, for my baby. He has really bad eczema. Anybody dealt with eczema? It's no fun. And I don't know if it's like a food allergy trigger, so I'm trying to go dairy-free for a week. Anybody live that life? The dairy-free?
It doesn't help.
Do what? It doesn't help?
It doesn't help. I've had eczema since I was born.
And dairy-free never helped you? Well, that's...
But I haven't.
Good news for me. I don't know. I read that 30% of babies that have it, it just kind of comes and goes. So it may go on its own, but food allergies could be a source of it. So I'm just
My sister's went away. Mine just didn't.
Oh, bless. Poor you. That's no fun. So anyways, if you have any dairy-free hacks, send them my way, please. But I'm not gonna buy dairy-free ice cream. I would rather make it. Okay, well, anyways, homogeneous mixtures. Vanilla ice cream is a good example. Okay, it's uniform throughout. Say every bite tastes the same, and there's multiple things we know in ice cream: sugar, protein, milk, air, water. Heterogeneous mixture, though, we know this. The moment you add some additive to your ice cream, be it pretzels or Oreos or M&Ms or whatever, that is now a heterogeneous mixture. It's not uniform throughout. Well, a solution is a homogeneous mixture, and solutions. We also have another type of homogeneous mixture called a colloid, and we'll actually look at the difference between these two. So what is the difference between a solution and a colloid? They're both homogeneous mixtures, but a solution has smaller particles mixed in, okay? So the thing that makes it a solution, the fact that there's more than one type of matter present, solutions have smaller particles, and colloids tend to have larger things dissolved in the solution or mixed into the solution. So these tend to have larger. It's a very weird G. Larger particles. Okay. Let's talk about milk for an example. We know, again, in milk you have things like sugar. Okay. A molecule of sugar, be it glucose or sucrose, is way, way, way bigger than an atom or an ion or a molecule of water. Also, we have proteins. Okay, so these are just two examples of biological molecules that are in something like milk. and they're a lot larger, a lot bigger, and that's what makes it what we call a colloid versus a solution. Solutions have things like ions in them, okay? Or small molecules like water. So anyways, that's the main difference. And this table down here really kind of outlines that. So it even gets down to the size. To be a solution, your particle size has to be less than 2 nanometers in, I guess, diameter. Anybody remember the size of a nanometer and how it relates to a meter? How many nanometers equals 1 meter? Do y'all remember? Also, I'm learning more this semester how bad I am at spelling than ever before. Or just writing while I'm talking. Not 1,000, not 1,000, much more than 1,000. How many nanometers in a meter? There's a lot. Nanometer is very small. Surely somebody remembers. Hannah, I can't count that many zeros. Is that 9 zeros? Should be 10 to the 9. Okay, a billion. All right. So nanometers are really small. So hence solutions, the particles are barely there. They're just really small. Okay, there's some examples of different solution colloid or even heterogeneous mixtures and how they're different. Colloid, those particles are much bigger. And then here is what I want to get to, the characteristics. And actually, I realize we need to fill in these blanks. A solution is a homogeneous mixture of ion or molecule size particles. It's a homogeneous mixture of ion or molecule size particles. And some characteristics of a solution, they're transparent to light. So what does transparent mean? Transparent does not mean colorless. It could be clear or it could have a color, but what is a transparent solution? What does it mean if it's transparent? See-through, Sarah said see-through, you can see through it. It's clear in the sense that it's not like murky, which is kind of what it says down here on colloids and on heterogeneous solutions. They're murky. You can't see through them. They're cloudy. Okay. Also, with solutions, there's nothing to separate. You can't filter anything out of them. If you left it standing in a glass, you wouldn't see something settle to the bottom. They're just the molecules are that small. They're going to stay dispensed throughout the liquid. But that's not necessarily the case with heterogeneous solutions. Colloids, they say that they're not filterable either, and that's the case with milk. Milk is a colloid. It sits in your refrigerator for a long time. You don't see 2 separate layers. That'd be gross if you saw that with your milk. Ew. Anybody ever had a drink of bad milk though before? Yeah, no fun. Heterogeneous as well, the difference with them is you can filter them out. There are particles large enough that if you leave it standing, they'll settle to the bottom. Oh, sorry, Angelina, what was your question? So like water, what's like water? Water is a pure substance. So, I mean, if you have water plus like salt mixed in, then you have a solution. Yeah, water is transparent to light. Absolutely. Talking about heterogeneous solutions, though, before we move on, I just want to point out it has blood, paint, other things as an example. I want to talk about your blood for a second because many of you are going into professions that you may deal with blood a lot, and you need to be aware of what's all in it. And maybe several things that are in it, but what makes this a heterogeneous solution? Okay. There's actually all kinds of stuff in your blood, and if we filtered certain things out, we could classify blood all 3 ways. If you filter certain things out, blood could be a solution and it could be a colloid. So what makes blood heterogeneous? What are like the largest things in your blood, do you think? RBCs, WBCs, red blood cells and white blood cells. Those are the things that if you leave it standing, they'll settle to the bottom. Things like plasma and platelets. Okay, these are the largest particles. And if we filtered all those things out, what would be left? Well, you would have things like proteins and sugars in your blood. You got blood sugar levels. These would make blood be classified as a colloid. These are colloid-sized particles. And if we filtered all of that out, then we would just have a solution of our blood. What is in our blood that's the smallest, do you think? Smaller than proteins and sugars? Water. Yep, you got ions, or we know them as electrolytes, okay? Sodium, chlorine, potassium, things like that. We have oxygen, air in our blood. So all sorts of things in our blood. And if you, based on if you filtered things out or not, you essentially would have all types of mixtures. Okay, so moving on. Anybody know what their blood type is? I feel like that's a question that like not everybody necessarily knows, but you should. What is the universal A plus basic? What is the basic? I've never heard of basic. I just have heard of the plus or minus. So like basic and advanced blood. Am I learning something new here? It's super normal. I didn't, oh. Just A plus, okay. Anybody know what the universal acceptor is? You should know. If you're a universal acceptor or donor, you're special. I'm almost a universal donor. A, B, is it positive or negative? I can't remember if it's positive or negative. I know it's an AB. AB negative, is that the one that's
It's AB negative.
That's universal acceptor? And then O negative is universal donor. So I'm O positive. All right, moving on. Solutions have two main parts. They have the solvent and you have the solute. Okay, so what are these parts? The solvent is just the part that's greater in or present in greater amount. Okay, typically it's a liquid, but not always. And it's what your gas or your solid, which is your solute, is dissolved in. And then the solute is the thing being dissolved. So two basic parts of a solution. A lot of people tend to think that a solid dissolved in a liquid, that's the only kind of solution we can have. But I kind of want to expand your brain for a second and help you realize there's all kinds of solutions. And you're more familiar with this than you think. We just don't think about solutions in this way all the time. So a gas and a gas. Well, atmosphere is a good example of that. Nitrogen is the most dominant gas in our atmosphere. So nitrogen would essentially be the solvent of our atmosphere. Oxygen, ozone, argon, and other things would be solutes dissolved in the nitrogen. Gas in a liquid. Y'all are also familiar with that. Seltzer water, club soda, my favorite. That is a solution as well. The CO2 being the solute and the water being the solvent. Anybody like a good club soda? Fresh squeezed lime in it. Oh yeah, all day. What else? Solid and liquid. Here's what we, solid and a solid. Metal alloys, so like brass or different things that are different metals mixed together, solutions as well. We tend to key in on this one, a solid and a liquid. But I just want to show you can have all kinds. All right, so we've talked about solutions. Now that we've defined them, there are principles that determine when something is soluble or not. Okay, soluble meaning when it will dissolve and when it won't. So just because you can mix things together, yep, I can go back. Just because you can mix things together does not mean you're going to get a solution, right? Anybody think of something, two things you can mix together, but they don't actually mix? Just because you pour them together, they don't mix?
Like oil and water.
Yeah. Oil and water is the common one we know. Anybody ever try to make your own salad dressing? You let like an oil with a vinaigrette type of something, and it's two different layers. It's my pet peeve when you're going to go pour that on your salad, but they're not mixed together and you just pour like straight oil on your salad. So anyways, how do you know what determines essentially when something is going to be soluble or not? Okay. because not everything is soluble. And to help us know this, we have a phrase like dissolves like. Like dissolves like. So this is a catchy little phrase. If you memorize it, it will help you because we're going to walk through some examples of some good exam style questions that you could expect on exam 4. Like dissolves like. What that means is if you have a polar or ionic, because ionic is something that's so polar that it's just a permanent separation of charge, right? So if you have a solute that is polar or ionic, it will dissolve in a polar solvent. Polar dissolves in polar. Like dissolves like. Example there, salt and water. You can think of many other examples. Sugar and water, okay? Non-polar dissolves in non-polar, vice versa, right? So if you have the example there, oil and gas. Non-polar solutes, they will dissolve in non-polar solvents. But because those two principles are true, it is also true that polar will not dissolve in non-polar solvents. Polar solutes will not dissolve in non-polar solvents, and vice versa. Non-polar solutes will not dissolve in polar solvents. Okay, like y'all said, oil will not dissolve in water. Now, I have a poll question because I want to see how well this clicked. All right, based on the concept like dissolves like, which of the following solutes would be soluble, meaning it would dissolve in acetone? Now you got to think about acetone for a second. You have CH3CO, CH3. And if you remember, we talked about acetone in chapter 8 as an example of dipole-dipole interactions, meaning molecules of acetone are polar. Molecules of acetone are polar. They are held together by dipole interactions. That was one of the examples we used when we introduced dipoles. So which of these 4 substances would dissolve in acetone, meaning which of these 4 are polar or ionic? $30 of 40, almost there. Give you another 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Anybody else want to vote? All right, end poll. Share results. Okay, most people got it. NaCl is polar, or sorry, it's ionic, so it will dissolve in acetone, which is polar. CH4, that's a non-polar substance. Carbon-hydrogen bonds are never polar. And even if it was, it would be symmetrical. Cl2, when you have 2 atoms bonded together, that's always a non-polar bond. The electronegativity difference is 0. So Cl2 is a non-polar molecule. Again, C2H6 is just carbons and hydrogens. So that's non-polar as well. So the only one that would dissolve is NaCl. Any questions on that? Remember, sodium cations, chloride anions. Okay. Stop sharing. All right, good. So the basis of this, honestly, to get a touch technical, why do polar things dissolve in polar solvents? It's because their intermolecular forces are similar. And that's exactly what this sentence is saying. Essentially, a solid will dissolve in a liquid, or a solute will dissolve in a solvent when you separate the 2 substances and you have pure solvent and pure solute, which is what we're looking at, like example in this figure down here. When you have the pure substances, you got to look at their type of intermolecular force. If we have water, and again, we know water's polar, okay? Hydrogen, oxygen bonds are polar, and we have that partial positive on the hydrogens, partial negative on the oxygen. We know that water will align itself, and the bonds that hold it together are hydrogen bonding, but that's because of the separation of charge. It's because we can draw these little partial positive, partial negatives in. And it's these things that are attracted to each other, right? Okay. So just in the same context, if we have NaCl as our solute, we know that this is held together by an ionic bond, okay, which is a permanent separation of charge, okay? This is the cation, and the chloride is the anion, okay? So because it's all based on separation of charge, which are similar concepts, these two things will dissolve together, okay? The solute and the solvent. But if they're not similar, then they won't mix. Now, when you have two liquids at hand, okay, when a liquid is soluble in a liquid, we call those liquids miscible. We say those liquids are said to be miscible. And if they don't mix, if you have two liquids, oil and water, for example, we call those immiscible. Okay. Two liquids that don't mix are immiscible. Liquids that do mix are miscible. Okay. So just for a little more practice, I want to look at these three examples. And the question is, will the following solutes, so the solute is listed first and the solvent is listed second. Will the following solutes dissolve in the following solvents? So let's look at these one by one. It's going to help you if you draw out the Lewis structure. You're just trying to determine, is my solute polar or nonpolar? And then is my solvent polar or nonpolar? And then you know they mix or they don't. So CH4 and water. Well, we already know water is polar. You don't even have to draw it out. What about CH4? What do y'all think about CH4? Carbon tetrahydride. Polar or nonpolar?
Non-polar.
Yes, Dakota. Nonpolar, yes, Janelle. We know carbon-hydrogen bonds are not polar. You could draw it out if you wanted. It just takes a second. We know it looks like this. None of these bonds are polar, so this is all day long. Non-polar. So are these things going, is this solute going to dissolve in this solvent? Remember, like dissolves like. Here we don't have two of the same things. It's so no. Okay. Look at the next one. MgCl2 and acetic acid. MgCl2. Let's talk about MgCl2. What kind of substance is that? Polar, nonpolar, ionic? Chanel said polar. What do y'all think? MgCl2. Dakota said ionic. So what kind of substance is Mg? It's magnesium. If you have a periodic table, where do you find magnesium? Group what? It's main group 2. Main group 2. So guess what? It's a metal. And chlorine is main group 7. It's a nonmetal. What kind of substance do you have when you have a metal and a nonmetal? Dakota said it. It's ionic. Okay. So up above where we said like dissolves like, we said ionic substances only dissolve in polar solvents. So if our solvent is polar, then yes, it will dissolve. If it's nonpolar, no, it won't. Okay, so acetic acid. Let's draw this out. This is not a condensed structure because we have the carbons all together and it's just not separated out in the CH3 groups or the CH2 groups that we normally see. So the way acetic acid looks is like this. If I wanted you to draw it out, I would give you the condensed structure. All right, there's acetic acid. So what do y'all think about acetic acid? Is it polar or nonpolar? So this all, don't forget Lewis structures, don't forget the polar, the whole discussion on polarity. Brendan says it's polar and he's correct, okay? If we split this molecule in half, like this, we could essentially say the left portion of the molecule is the electron poor side, so it's going to have a partial positive. The electrons are going to be drawn over towards the electronegative atoms, which are oxygen. So we would say this is the electron-rich side. So if we were to draw a dipole in, you draw it pointing towards all those oxygens. Yeah, and the hydrogen-oxygen bonds are polar as well. So this is definitely polar. So will they mix? Will this solute, magnesium chloride, dissolve in acetic acid? Aubrey, I can barely tell, but it looks like you're shaking your head yes. All right, yes, they will. All right, last one, CH2Cl2 in methanol. What do you guys think? What do you think about CH2Cl2? Is this polar or nonpolar or ionic? Anybody? Nobody wants to guess. Nobody wants to be wrong. Polar question mark? Polar. Yes, it is polar. Sorry. This one's tricky. This one looks polar because those chlorines, but you can actually draw this out two ways. Let's draw this out both ways. You could draw it out like this, or you could draw it out like this. And yeah, we know those chlorines should get all their lone pairs. Now, what do you think? Nonpolar. Here's the deal. We can draw dipoles in, right? Because the carbon-chlorine bond is polar. These bonds are polar, so we could draw dipoles like this, pointing towards those chlorines. But it's, yes, Sarah, it's symmetrical, so those cancel out. But what about this one over here on the left? What about that? Here's the disadvantage we're looking at a two-dimensional structure, okay? Molecules are 3D. These are actually the same molecule. You're just looking at it from a different view, okay? The one on the left, I could rotate it so that it looks like the one on the right, but it's the same structure. So if you can draw it so that it's nonpolar, that molecule overall is nonpolar. Those dipoles will cancel out, okay? So overall, CH2Cl2 is nonpolar. Did everybody just catch that? That's it okay with everybody? All right. So what about methanol? Is methanol polar or nonpolar? Here's methanol, CH3OH. Well, we know OH groups are a very common flag here that it's a polar molecule, unless there's symmetry. So this is definitely polar. We know the oxygen-hydrogen bond and the oxygen-carbon bond are polar bonds, and we got lone pairs. You could draw a dipole in, okay, pointing like that towards those oxygens. This would be the partial positive region. This hydrogen is also a little partial positive. And this would be the partial negative, all right? So overall, this is methanol's very polar. So you got nonpolar and polar, which means, remember, polar and nonpolar, they don't mix, do not dissolve. So the answer here is no. All right, any other questions on that? This is definitely a good style of exam question. I like this because you really got to think about it and you gotta understand the concept to answer these. To help you out with stuff like this, I'm just going to give you a list of very common polar solvents and common nonpolar solvents so that maybe if you actually know this or have this slide available or close by on exam day, you don't necessarily have to take the time to draw everything out. Okay, little shortcut. So polar solvents. One would be, anybody know of what I should write first? The most common polar solvent is what? Water. Yep. Okay, water is a very common one. Number 2, acetone. We drew acetic acid, but acetone is a very common one, and acetone is this. It's CH3 CO CH3. So it essentially looks like this. Okay, and there is a dipole, boom, that way, pointing to that oxygen. That's the polar bond. So acetone's 1, and then these up here, acetic acid and methanol. These are both very common ones. So that's going to be 3 and 4. We already drew those out up above, so I'm not going to redraw those. And 5, I'll give you one more, ethanol. Ethanol is very similar to methanol. So methanol was a CH3 group, and then an OH, it's right up here. And ethanol is just another CH3 group. Or really another, looks like this. And there's a CH2 group, and then there's O and H. Okay, anytime you have this OH group, which we know OH is what? It's hydroxide, okay, from your polyatomic chart, hydroxide, OH minus. Anytime you have that in a molecule, the ending of the molecule name is OL. Methanol, ethanol, propanol, butanol, okay? They all have an OH group, and we'll get to that when we look at functional groups, which will be the very last thing we look at this semester. Not that you have to memorize that, just so you know. Some common nonpolar solvents, though, one would be carbon tetrachloride, CCl4, carbon tetrachloride, carbon with 4 chlorines, and all these dipoles cancel, so overall the molecule is nonpolar. So carbon tetrachloride, another one called benzene. This is actually C6H6. This one looks really weird. It's actually like a hexagon. Looks like this, and then there's double bonds between these carbons, and then each of these carbons gets 1 hydrogen. This is benzene. You'll also probably recognize this guy when we get to functional groups. But it's very nonpolar because it's just carbon-carbon bonds and carbon-hydrogen bonds. But it's a very common nonpolar solvent. And then 3, diethyl ether. And so ether groups are like this. This is the last one. There are 2 carbon groups. Then you got an oxygen in the middle, and then you got another 2 carbon group. So because it's symmetrical, those dipoles pointing towards oxygen would cancel. There should be dipoles right here, boom and boom. And because they cancel, that molecule is nonpolar. All right, so just a little list. That way, if I ask you on the exam and you recognize one of those names, you just come over here and say, oh, this one's polar, this one's nonpolar. And then you're just judging the solvent, or sorry, the solute. Any questions before we move on? I think it's good to be aware of these. You'll probably realize once you know the names that you come into contact with some of these things more than you think. Okay, solubility limits. So we kind of talked about some rules here as far as when things are soluble and when they're not. With everything that is soluble, you can really only dissolve it up to a certain amount. Okay, there are limits on how soluble something is. So if we are dumping salt in water, that's my example here. You can dump salt in water and you can stir it, and you can dump more and you can stir it. And then eventually you're going to dump so much that you can keep adding salt, but it's not going to dissolve. Here's what's happening when you dissolve salt in water. We know salt is ionic, so you have all these cations and anions. They arrange themselves, okay, because all the green spheres are negatively charged and all the purple spheres are positively charged, because your purple is your sodium, your green is your chlorine or chloride anions. So they're this nice ordered crystal. Well, water molecules come in and they bump into this and they interact with it. And because there's attractive forces between the cation or the anion and the water molecule, if you get enough of those attractive forces, it floats away with an ion. And then that ion is dissolved. Okay. That ion is dissolved. Okay. That's what they look like. They're surrounded by water molecules. Well, if you run out of water molecules because all of them are already interacting with a dissolved ion, then you have no more ions that you can dissolve. Okay. And that's when you've hit your solubility limit. So that's essentially what we're saying here. There's a limit to how much solute can be dissolved, and the max amount of solute that can be dissolved, we call that the solubility. That is the substance solubility. And we express this as grams of solute. So it'd be like grams of salt, NaCl, per 100 milliliters of solvent. So I think, if I remember from this morning, it's 36 grams of salt per 100 milliliters of water. That's actually the solubility limit of sodium chloride. Now, once you've hit that limit, you have what we call a saturated solution. Okay, a solution that has hit its solubility limit is saturated. And then if you keep adding solvent, you have a super saturated solution. A really good example of this, anybody buy honey and you keep honey on your shelf for a long, long time, what happens to the bottom of the bottle of honey or container of honey?
All the sugar goes to the bottom.
Yes, it starts to crystallize on the bottom, right? And then you're like, shoot, I got to go microwave it and get it all mixed up again if you want to use the rest of it. How many of you are like, I'll just throw it away at that point? I'm like, no, I have to get every drop. So honey's a good example because there's so much sugar. It's a very super saturated solution, actually. Sugar being the solute that's dissolved in the honey. So we're actually going to talk about how you can kind of bend solubility limits because to every rule in chemistry, there's always a way to break them, okay, or bend them. Before we move on, though, when we're dissolving solutes and solvents, can you go back? Yes. When we are dissolving solutes into solvents, is this a physical or chemical change? This goes all the way back to like the beginning of semester when we talked about how do you know if something is chemical or physical? When you're dissolving a solute in a solvent, is that chemical or physical? What do you think? Physical, yes, Janelle, physical. We are not creating a new product. We're just mixing things, okay? You still have the same two things or more than two things even. They're just redistributed throughout the solution. All right, any questions so far? Angelina, are you good? Okay. All right, increasing solubility. So this is for all you rule breakers out there. Who's a rule breaker? Who's like, rules were made to be broken? That's the way I see things. Who is my rule follower? Any rule followers? You're like, why would honey be considered heterogeneous? Sarah, I think honey would be considered homogeneous. Here's why. Every bite of honey tastes the same, or it should, right? And so the mixture is uniform throughout. Things are evenly mixed throughout the mixture. Unless if you don't have it crystallizing at the bottom. So honey is a homogeneous mixture because every bite tastes the same, kind of like vanilla ice cream. Just because it's crystallizing, that doesn't make it heterogeneous. I don't think. It would still have the same. You might have a higher concentration of sugar down at the bottom. That's actually a great question. At that point, maybe the uniformity is not consistent throughout. So I bet technically you probably could call that a heterogeneous mixture at that point. But you would really have to define a crystallized solution of honey or mixture of honey versus a non-crystallized. Okay, anyways, increasing solubility. I hope that answered your question, Sarah. Solubility has limits, and we know we define solubility as grams of solute per 100 milliliters of solvent, but we can manipulate solubility with temperature. So sticking with our honey example, pun intended, what can you do to redissolve all those sugar crystals? Pop that thing in the microwave, right? Heat it up, stir it, the sugar should redissolve. Now, that's because sugar is a solid. And so we actually have to define here what our solute is. When we have a solid dissolved in our liquid, meaning this is our solid solute, this is the solute in both cases, the liquid is the solvent. When you're talking about a solid like sugar dissolved in something, the solubility of a solid increases as temperature increases. Okay. Anybody drink sweet tea or tea? This is the South. I grew up on it, but I really don't drink it anymore, if I'm being honest. So if you go to a restaurant and you get a glass of iced tea and it's just not sweet enough for you, so you grab one of those packets off the table and you shake your packet, okay, and then you pour it into your tea. Here's what's always frustrating about that is the tea is usually cold, so the sugar like just settles to the bottom, right? Even though you stir it with your straw a bunch. You stir it and you stir it and then you leave your tea there and all the sugar settles to the bottom, right? And then you get a big old drink of straight sugar and it's really gross. But if you had hot tea, if you had a gallon of hot tea and you dumped a bunch of sugar in that, what do you think would happen? Would you have to work as hard to get that sugar dissolved? Absolutely not. You know it would dissolve. And that's the example here. So sweet tea. Sugar readily dissolves with heat in a hot solvent versus a cold solvent. Okay, so the higher the temperature, the higher the solubility. All right. Again, with the honey, if you have a supersaturated solution, you can increase the solubility limits. You could maybe even dissolve more, pass beyond the solubility limit if you heat the solution up. On the flip side, gas is dissolved in a liquid. So we're going to go back to the example with club soda or like seltzer water. You have a gas dissolved in a liquid. Really, you could think of any carbonated drink. So if you like Coke or Pepsi, or any carbonated drink, you've got CO2 dissolved in the liquid, right? That's what makes it carbonated. And if you have that in the refrigerator versus if you have it at room temperature and you open both of those drinks, which one has a higher amount of fizz to it? A cold carbonated drink or a gross lukewarm carbonated drink? Definitely the cold one. Okay. It was really frustrating. One time I bought a whole pack of, we're fancy at my house, Kroger brand, club soda. And I left it in the car on accident overnight, and it was in the summer. And we put them in our fridge later. I was like, oh, they're fine. We'll just put them in the fridge. Well, I should know this because I teach this class. We opened all those cans and like they had all lost their fizz. Okay. Even though we had cooled them down after that, they just got too hot. So what that illustrates is that a gas dissolved in a liquid, here's what happens. Solubility of a gas decreases as temperature increases. The example here is carbonated drinks. Okay. More CO2 is dissolved in colder drinks than it is in warmer drinks. Questions on that? All right, these are just graphical representations, these next two slides, of exactly what we talked about. Okay, so this is exactly what we talked about, just represented on a graph. Solid dissolved in water. We have many different solids here. Glucose, which is sugar. Sodium nitrate, I don't even know how to pronounce that actually. KBr, potassium bromide, copper sulfate, sodium chloride. And what you see for the most part, you have a few anomalies down here. Their solubility doesn't necessarily increase as you increase temperature, but the x-axis is temperature. So as you go up in temperature, 60, 80 degrees Celsius, the solubility, which is the y-axis, and notice it's grams per 100 ml. You just got to turn your head sideways. Grams per 100 ml solubility, that's the y-axis. That is increasing. All of these curves, these colored lines, represent the solubility of these substances in water. So if I were to ask you, I'm pretty sure you have a homework problem that's geared like this. If I were to ask you, what is the solubility of glucose in water at 30 degrees Celsius? Could you tell me? Glucose is this red data here. Well, where's 30 degrees Celsius? It's right between 20 and 40. All you do to read solubility off of the graph is you take your x-axis and you essentially extend it up. You follow that temperature up until you hit the data line for whatever substance it is. For here, we're talking about glucose, so we extend it up till we hit the red line. Then you're going to follow that over until you hit the y-axis. Okay. So solubility at 30 degrees Celsius would be what? 120 grams per 100 ml. You use these units, 120 grams per 100 ml. So 120 grams of glucose per 100 ml of water. That is the solubility of glucose at 30 degrees Celsius. Again, if I ask you what is the solubility of copper sulfate at 70 degrees Celsius, we'd go find 70 degrees Celsius, extend that up until we hit the data line for copper sulfate, and then you would essentially see where that hits the y-axis. I would say roughly 50 grams per 100 ml of water. Okay, so I'm pretty confident that there is a homework question where you have to read solubility off a graph, and that's how you do it. And then this bottom graph is just the same thing, but for gases. And you see the trend is opposite. As you increase on the x-axis, increase in temperature, what happens to these data lines? They go down, and that's showing you that solubility is decreasing as you increase in temperature. As you go further right across the graph, the solubility goes down, 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 down. Okay. Questions on these? All right. We're doing much better on time than we were doing this morning. So I'm going to see how far we can get. We're going to do Henry's Law, and then I bet we can get to units of concentrations, and that's probably all we'll hit today. Oh, that picture makes me queasy. I can't look at that stuff. Can't do needles. Okay, Henry's Law. This is a law very similar to, say, Charles' Law, Boyle's Law, Avogadro's Law. But it's relating concentration of a gas dissolved, the solubility of a gas as you change pressure. Okay. So the concentration, which is another word for the solubility of a gas, is directly proportional to the, I think it's partial pressure. To the partial pressure of the gas when the temperature is constant. Okay. So pressure essentially can affect solubility. Increasing pressure can increase solubility of the gas. The more the pressure, the more gas that will be dissolved. This is why they give us drinks in a sealed closed container. Okay, if you think about a Coke or a Sprite or whatever, the moment you crack the can open or open the bottle on the, or open the lid on the bottle, a bunch of gas is released because you just decrease the pressure. That bottle is very pressurized, and they want the gas to stay in the liquid. And then the moment you decrease the pressure, you're gonna let loose a bunch of, you'll see the bubbles float to the top, right? Especially if you shake it, then you're gonna lose a ton of gas because you decrease the pressure, so you decrease the solubility. In mathematical form, here's what Henry's law looks like. C1 over P1 equals C2 over P2. And we know C stands for concentration here. So that's your initial concentration at your initial pressure is C1 and P1. And then C2 and P2 is your final concentration at your final pressure. So if you change the pressure, you got to recalculate the concentration. Here's just a picture of that. If we have a system at equilibrium, you see these red spheres are your gas particles. And you have equilibrium. So you have 2 arrows going up, 2 arrows going down, indicating equilibrium, because we know equilibrium is forward and reverse rates at the same rate, okay? So you have gases leaving the liquid at the same rate gases are going into the liquid. Well, if you push down on the lid, you increase the pressure by pushing down on the lid. Notice now we have a bunch of downward pointing arrows. You're going to force more gas particles down into the liquid. You're going to increase the solubility. And then we'll eventually restore equilibrium. But at that new pressure, you'll have more gas particles in the liquid, okay? Higher solubility. All right, let's actually work a Henry's law problem. And the units for solubility, remember, the units for concentration are grams per 100 ml. And when we work this problem, you will not actually, I know there's a number within our units here. That's very bizarre. We don't normally have numbers in units. Numbers are usually separate from units. Here you have a number in your units. You're not actually going to divide by 100. You're going to leave it alone, okay? Treat it as though it's just letters. Here's what I mean. Okay, let's read this problem. When the pressure of oxygen is 159 millimeters of mercury, that is a unit of pressure, so this is P1. It says the solubility of oxygen in blood is 0.44, and here's our units, gram per 100 ml. What is the blood solubility at 11,000 feet elevation? We know that pressure, as you go up in elevation, atmospheric pressure decreases, okay? So if you're standing on the top of Mount Everest, you have less atmosphere pushing down on you, remember? So if pressure decreases, what do you think is going to happen to concentration? So we're higher in elevation, and there the partial pressure of oxygen is 56 millimeters of mercury. So we went from 159, and here's P2, down to 56. And then this original solubility, this is our C1. So again, I like to go in and label these problems. I'm going to turn my screen sideways. I bet y'all could see it all at once. See it better. Okay, so let's work this problem. We've got C1 over P1 equals C2 over P2. And it says, what is blood solubility? So because it's asking us this right here, this is C2. We don't know C2. So we're going to look for C2. So here's our equation. And just like Boyle's or Charles or Gay-Lussac's law, you have to first rearrange your equation to solve for the piece you're missing. So I'm going to get C2 by itself. So I'm going to cross multiply both sides by P2. Okay, so then P2 cancels on this side. And our new equation is P2 times C1 over P1. So the final pressure times the original concentration divided by the initial pressure, that is going to give us the new concentration, the final concentration. Now we just plug everything in. So P2 is 56 millimeters of mercury. So we'll do 56 times C1, which was 0.44 grams per 100 ml. And again, you will not divide by that 100. Don't do it. Leave 100 alone. It's just part of your units. And then you're going to divide by the initial pressure, which is 159 millimeters mercury. And then what happens to millimeters of mercury? Those units cancel, and you're left with units of gram per 100 ml, which is what we need. That's units of concentration. So 56 times 0.44 divided by 159. 56 times 0.44 divided by 159. Anybody get it? Caitlin got 0.155, and that is grams per 100 ml. So what happened to the solubility? As pressure decreased, solubility was 0.44, and now it's 0.15, roughly a third. So it decreased by 2/3. So as you decrease pressure, you decrease solubility, and vice versa. As you increase pressure, you increase solubility. Any questions on that problem? Man, we're really doing good on time. Okay, let's talk about units of concentration, and then that might be all we really get through today. We'll see. Okay, we actually introduced this slide when we talked about chapter 7, when we introduced equilibrium. Because in our equilibrium constant expressions, we were using units of concentration. Concentration is just an amount of solute per a volume of your solution, okay? Not solvent per volume of solution, and the solution is the solvent and the solute combined. So there's two different ways you can communicate concentration. Two major ways, we'll put it that way. You can do weight volume percent. We abbreviate that WV percent. We also, the nickname is the mass volume percent. This is going to be grams. Well, I'll write out the whole word. Grams of solute per milliliter. Do not get that confused. Don't put in liters. You have to put in milliliters of solution. And then to turn it into a percent, you do that times 100. Weight volume percent. So you do the weight in grams of your solute on top, divide that by milliliters of solution, and then you do times 100. And then you also can communicate concentration in molarity, which is moles of solute per liters of solution. So a little different, and you don't multiply by 100. Nurses, you'll have to communicate with molarity quite a bit. Different stock concentrations of things you get. I actually had a question. My brother-in-law, he's an engineer, and he literally was doing weight volume percent stuff yesterday. I was like, hey, can you help me with this? But you work with molarity. An example is when you take urine samples, and oftentimes dialysis lab work, you have to communicate the concentration of different electrolytes or different things in urine samples with units of molarity. Okay. So that's units of concentration. We're going to do a lot of practice problems with that. By the way, last thing before we work some problems is when you go to prepare a solution, there's actually a particular way you go about it. You can't just dump in your solvent and dump in your solute. It's more technical than that. So you have to first, if this yellow powder is your solute, you'll dump it into, this is a volumetric flask, you would dump it into your container. Then you put a little bit of your solvent. So then you add some, not all, but some solvent. And you mix it up. Then you finish adding your solvent. I feel like this is really hard to read. Add rest of solvent to final volume. Okay. So you're going to add some of the solvent. You don't want to go past the total volume though, and you have to remember some of the solute takes up volume as well. So you put your solute in, add some of your solvent, mix it, dissolve all your solute, and then you fill it with a solvent to the final volume. That's the technical way you should go about it. I really would love to skip over this slide. All this is saying right here, I'm just going to go breeze through it real quick. If you have a solid solution or solid, for example, a solid solute and a solid solvent, what would you express units of concentration in? Okay. If you were doing weight volume percent, it would be not weight per volume, it would be weight per weight, essentially. Whoops. Because you have two solids. So you would do grams of solute per you could use grams or milligrams, grams of solution. Okay, because you're talking about solids, and grams, weights, talk about solids better than units of volume. Volume is for liquids. On the flip side, if you have two liquids, instead of grams and grams, you could use milliliters of solute and milliliters of solution. Okay. So you just need to make sure, all this is trying to illustrate is that you need to make sure the units match the state of matter that you're dealing with. Okay, grams and milligrams and things like that are for solids. Milliliters and liters, things like that are for liquids. Okay, let's actually, with the time we have left, let's just work these two problems and then we're going to be done. So hang with me. We're going to use this weight volume percent equation and we're going to work some problems. So this first one says, what is the concentration in weight volume percent of 15 grams of glucose dissolved in 100 milliliters of solution? What is the concentration in weight volume percent if you have 15 grams of glucose and you have 100 milliliters of solution? So we're just going to plug in 15 grams on top, 100 milliliters on bottom. You're going to multiply by 100. So weight volume percent equals 15 grams of, I'm going to use capital G for glucose, over 100 milliliters of solution times 100. What will our percent be? Yep, Caitlin said 15. Essentially, the hundreds cancel out. When you divide and multiply by 100, you're left with 15. So your weight volume percent is just 15. So that would, so people might say that's a 15% glucose solution. Okay, you might hear somebody say that, 15% glucose solution. Okay, if I dissolve 180 milligrams of heparin, anybody know what heparin is? What is heparin?
Keeps your like things from clogging.
It keeps your things from clogging. It's an anticoagulant. Caitlin works in a hospital, in case y'all didn't know. So she knows these terms. Yeah, I actually worked a lot with heparin in grad school. It keeps your blood from clotting. It is a player in your blood clotting system. Okay, so if I have 180 milligrams and I dissolve it into 15 milliliters of solution, what is the weight volume percent? Now here, take note, we've got to first convert this to grams. You can't just plug in because it's in milligrams right now. So we need to convert it to grams and then we can plug in milliliters just fine. So let's convert 180 milligrams of heparin to grams. So there's 1,000 milligrams in 1 gram. So divide by 1,000, you should get 0.18 grams of heparin. So now we can use that and we can plug that into the top part of our equation. So the weight volume percent is going to be 0.18 grams of heparin divided by 15 milliliters. And then don't forget, you got to do times 100 to turn it into a percent. So 0.18 divided by 15. .2 weight volume percent. Okay, so it'd be a 1.2% heparin solution. All right, any questions on how we did those? Okay, well, there's definitely way more practice problems, a whole 3 more slides. So I would say if you want to, we'll use these as review when we get ready to prepare for exam 4. But I would say try to attempt these on your own. They're really quick, I think. If you just use the equation, just make sure you're plugging in the right units and try to make sure you understand this pretty good. I'm going to do the last little poll that I've done before, kind of the review poll. I want to know how well did it go for you today? You feel like you're understanding quite a bit of this stuff, or was this stuff super confusing for you? All right. I would say today was the easier portion of chapter 9. I'm going to give you guys a heads up. Tomorrow is going to be more involved. Tomorrow, Tuesday. Tuesday is going to be more involved. So make sure you have your caffeine and you're ready to go Tuesday because it'll be a little more in depth than what we did today. Okay, so most people grasp quite a bit of it, 75 to 100%, but we have a few people that are feeling like, I only got 50% or less. And if that's